Welcome back to part 2 of chapter 1. I realized I went really slow in the first part. I think I talked too much because I only got through 13 slides or something. So yeah, super sorry for being a very long-winded individual. My fault. So what we're going to go into now are characteristics that are associated with all humans. We already talked about how we're organized. We talked about the organization levels. Then we talked about how these different organization levels bring out the organ system, and that organ systems we talked about come together forming that whole organism. Now we're going to talk about metabolism. So metabolism, in a nutshell, is the sum of all the chemical reactions that occur within your cells, okay? And so there's a lot of different reactions, and we can break them into two broad categories, anabolic reactions and catabolic reactions. So when I think of catabolic reactions break things that are large into smaller subunits. So you take large molecules like proteins and you break them up into those amino acids. I like to remember this by just remembering that cats, and so if you have a cat, you know this. If you don't have a cat, you probably still know this because you probably know somebody who has a cat. Cats like to jump on your counters or on your shelves and they break things. They jump up and things fall down and break, and you're like, well, that just sucks, right? So catabolism is the breakdown of large molecules into smaller subunits. Cats break things. When we break things down from larger to smaller, we release energy. Anabolic reactions, then, anabolism, is the build-up. So you take small subunits, you put them together, and you build something larger up. That's an anabolic reaction. Anabolic reactions take in energy. And I always remember anabolic reactions because most of you, hopefully, I don't know if it's hopefully or just most of you probably is probably the better word, have heard of anabolic steroids. Anabolic steroids build muscle up, so anabolism builds molecules up. And I have my own pictures that I like to use. So here I just took, more Google images, but what I did was I took a bunch of different substances that typically are found in cake, and you take these, you put them into a big bowl, you mix them all together, you pour them into a pan, and you put them in the oven. You add some heat energy because anabolic reactions require energy, and you make this larger molecule. So these are all the subunits that make up this cake. We put in some energy, and now we have this beautiful, tasty cake. Catabolic reactions then are opposite of this. Oh, I totally did not do that. Sorry. Hold on. Okay. There we go. Sorry about that. So catabolic reactions, then you take that large subunit, you break it back down into its smaller monomers, smaller subunits. And so here we have a child eating the cake. And in that process, we release energy. And so that child then can go out and play. And obviously these pictures aren't the same child and it's not the same cake. It's just a pictorial view of anabolic and catabolic reactions. So hopefully you like it. It's the easiest way I know to explain this process. But both of these anabolic and catabolic reactions are under that larger header called metabolism. They're both metabolic reactions. And here's another example of metabolism at work. So your body is producing, taking and breaking down carbohydrates, glucose specifically, and releasing energy. That energy is then driving your muscles to be able to move. And so these marathon runners are able to move in response to the release of ATP energy through that catabolic reaction. So they're releasing energy, and the energy is allowing them to move. They're also responding to stimuli. So you might not really be able to see it on their bodies, but there's you can kind of see the sheen on their heads because they're going to be sweating. That sweat is helping to maintain body temperature. So they're responding to an increase in body temperature by sweating. And so this is also responsiveness, and then of course their bodies are moving. So that's another characteristic that living humans have. We all respond to stimuli. We all move. So internally, we have blood vessels that are constantly contracting, relaxing, moving blood. Our digestive system is constantly moving. Externally, we have our arms, our legs, our head is always moving. Our tongue moves when we want to talk. We have to move our mouth to eat, or to speak. We grow and develop. So we start out, what they didn't show you over here, is that we started out as a single-celled zygote. A zygote is a single cell composed of 46 chromosomes. 23 came from mom, 23 came from dad. That zygote then started to replicate under mitosis, mitotic divisions. And those cells, as the organism grew, those cells started to specialize. And so we had 3 different regions, an endoderm, an ectoderm, and a mesoderm. And then those specialized regions started forming our organ systems. And eventually we had this little tiny baby organism right there that eventually will grow and develop into a young man who can then reproduce himself, that doesn't sound right, reproduce with another to produce new offspring. And eventually, as he develops or as he grows older, his cells will start failing him, and he'll become an older person that may not function as effectively as when he was younger, because that's what happens. And it's a cute little picture showing, how we start out as tiny little things and how our bones start to compress, and we start getting shorter as we get older as well. So just kind of cute. Here you can see that mitotic division that I was talking about. Here's a male, here's a female. Male produces the sex cell called sperm. Female produces a sex cell called an oocyte. Sperm and egg come together, forming that diploid zygote. A zygote undergoes multiple mitotic divisions, forming this ball of cells that eventually will differentiate into different regions, ecto, endo, and mesoderm. And those will specialize into forming different organ systems, eventually forming that offspring. Humans are also highly adaptable. Now, I say adaptable, we adapt. The adaptations that we tend to think about are called microadaptations. A true adaptation is on the genetic level, so it's in our genes. But we do adapt to changing temperatures. So an example of adaptation to changing temperatures, when the temperature starts to cool off, we tend to put on more layers. When the temperature starts to get too hot, we take off layers. In this case, the temperature is extremely high, and so these individuals are covering themselves in a white layer. The white layer will reflect the sun so that it doesn't get absorbed as easily. They also are going to, depending on how often they're in these high temps, their sweat glands are going to be able to respond more effectively. so that they can then sweat and keep themselves cooler. But if it's a high moisture environment, which deserts tend not to be, then they're probably not going to sweat as effectively, because if it's a very moist environment already, high humidity, then you're not going to be able to get rid of that sweat off of your skin. The sweat's not going to evaporate because there's so much moisture in there anyways, and so you're not going to cool down that way. Here are some other examples of how we help to maintain our different, our body temperature or the amount of oxygen in our system. We are able to maintain oxygen levels or maintain body temperatures through a process called homeostasis. And so we will accommodate depending on the environmental pressures that we have, literal pressures or, just figurative pressures. So in this picture, you're seeing Mount Everest, which is very cold. So individuals that are going to be climbing Mount Everest, they're going to want to make sure that they are layered with clothing. And they're going to do that, but they don't want to have too many layers on, because if you have too many layers, then it's going to be too hard to climb. So they have to make sure that they can maintain that level of warmth with the ability to still move. Low oxygen levels, because you're so high up, you're going to have less pressure in the environment, and the way oxygen gets into our lungs is by pressure. So the only reason we can breathe oxygen in and exhale oxygen out is because the pressure's difference in the environment, in the atmosphere, is higher than the pressure in our lungs, so we can breathe in. And then when our pressure in our lungs is higher, then we can exhale. So I've changed the pressures in my lungs to either increase the amount of pressure in my lungs or decrease the amount of pressure in my lungs. Atmospheric pressure doesn't change. But if we move up in the atmosphere or if we move down in the atmosphere, that pressure will change. Higher up in altitude, you have lower pressure. So oxygen is not going to diffuse as easily. It's not going to move as easily. And because of that, humans have actually adapted to produce more blood at those levels. If you are a climber that goes to Mount Everest, you might not produce, so likely if you live in, say, Illinois and I'm going to go climb Mount Everest, you just leave to go climb Mount Everest, you're probably going to struggle with that change in altitude. But if you live in the mountains, if that's your normal environment, then your body has adapted to produce more blood. The more blood you have, the more oxygen you can take in per inhalation. And that allows you to survive in those lower pressure, higher altitude environments. So what is it that actually allows us to maintain oxygen levels or maintain body temperature? That term is called homeostasis. Homeostasis is the maintenance of a stable internal environment. That's what it is. So we're constantly having stimuli that come in, and they try to change wherever our set points are. Think about when you woke up this morning and you were laying in bed and you sat up. Immediately your blood pressure started to drop. You changed position. But your body responded by increasing blood pressure. So blood flow goes to the brain so that you can move. When you get ready to exercise, or when you're in the middle of exercise, you need more oxygen getting to your cells so that you can produce energy. The only way you can do that is if your blood pressure increases to push blood faster through your system so that your cells can gain those things. Because remember, your blood and your cardiovascular system, in that sense, is what moves nutrients. Oxygen is a nutrient. Oxygen comes in when we breathe, and then it's going to get pushed around our system through our blood vessels. So we have to be able to maintain multiple set points. Blood glucose levels, blood pressure levels, water balance, acid balance, thirst. We have to maintain nutrient levels, so hunger. We have to continuously know where our head is in association with the ground. So we have to be able to maintain equilibrium. So there's a lot of things that are constantly changing, but we have a lot of set points that our body maintains, and that's homeostasis. Homeostatic mechanism contains three major parts: the receptor, the control center, and the effector. The receptor is what takes in information, takes in a stimulus and says, this is weird, this is not right, or this is different than what it's supposed to be, and sends that stimulus to a control center. Control center, typically our brain or our endocrine system, is going to determine what needs to be done, if anything needs to be done. And then that information is going to move to an effector. The effector is going to be muscle or glandular tissue that will bring about some change. So anytime you are not in homeostasis, that's what this imbalance bar says, the receptor picks up that change, sends it to the control center, which sends that response or sends a message to the effector that will bring about a change to bring you back to homeostasis. My favorite example is, and I guess it's my favorite example because it's one that I'm very comfortable explaining, blood glucose levels. So you all know what, or I shouldn't say that, because one day there's going to be someone that says, no, I don't know what it is. But in general, most people know what diabetes is. They know that diabetes, they might not know how it works or anything, but they know that diabetes is a disease where you don't maintain blood glucose levels. You can't maintain proper blood glucose levels. Most people, if you don't have diabetes, you can eat 5 jelly donuts in a row. Woo, and then you get all this sugar rush and you're like, woo, woo, woo. But if you were to take your blood sugar levels will be maintained where they're supposed to be, between about 70, maybe 90. They might go up a little, no big deals, right? But if you're diabetic, that doesn't happen, because diabetics can't maintain their normal blood sugar levels. And so how do we maintain our blood sugar levels? What happens is, as soon as we start taking in that sugary substance, in this case, jelly donuts, our blood sugar starts to spike, and that spike in blood sugar is going to lead to receptors in your blood sending signals to your pancreas. Your pancreas says, hey, there's a lot of sugar in my blood. We need to do something. And the pancreas releases insulin. Insulin then moves into the blood and pulls all of that glucose out of the blood and puts it into our cells, our liver, our muscle. If there's too much sugar, then it moves it into fat even. And so then that blood sugar is no longer causing problems. Now, what happens if you don't eat? So everybody has had a day where they skipped breakfast or skipped lunch. Maybe you were working through it. Who knows what was going on? Maybe you just didn't even realize that breakfast or lunch were past. Maybe you slept through breakfast. Who knows, right? So you go through and your blood sugar levels start to drop. So at some point, sugar levels start to decrease. And again, receptors in your blood say, oh my gosh, this isn't right. Our blood sugar levels are dropping. and they send signals to the pancreas. The pancreas is this awesome organ that just maintains blood sugar levels as one of its functions. So as soon as the pancreas gets that signal from the receptors, the pancreas, which is the control center, sends out glucagon. Glucagon is another hormone, but this hormone tells your cells, the same cells that took in the glucose, to release that glucose back out. So your cells took in glucose, they built up this molecule called glycogen, and now they're going to break down that glycogen and release it back into the blood so that you now can bring your blood glucose levels back to homeostasis. That's how homeostasis works. There are two types of homeostasis. Negative feedback, which is the most common form of feedback, and then positive feedback. Positive feedback is not as common, but it's still very important. In both cases, we are bringing our bodies back to homeostasis. So with negative feedback, here is a set point. It starts, some stimulus starts to move that set point away from homeostasis, or that variable away from homeostasis. With negative feedback, we're just going to oppose that set point, or that variable, and bring it right back to where it's supposed to be. That's negative feedback. We oppose the change and bring it back. In positive feedback, we encourage the change. So as we're changing, we start pushing with that change. We push and push and push until we snap back into homeostasis. So some climactic event will occur. Here's body temperature with negative feedback. So you have some stimulus that is detecting a change in body temperature. It's picked up by your receptors. The receptors send a signal to your control center. Control center then sends a signal to the effectors. In this case, our body temperature has increased above normal. So 37 degrees Celsius is normal body temperature. In Fahrenheit, it'd be 98.6 or so. This is going to be detected by our skin. It'll be detected by, mainly, like, your skin is going to detect that change, right? Internal organs might detect that change as well. That change in temperature is going to be sent to the brain. The hypothalamus, which is your temperature regulator, then sends a signal to your sweat glands, which are part of the or one of the accessory organs of our skin. And the sweat glands start to sweat, start to release sweat. That sweat goes to the surface of our skin and helps to cool the body off. As it evaporates, it pulls away the heat. This is just a cuter image of what you just saw over there. In this case, we have increased body temperature or decreased body temperature is going to be picked up by our stimuli. Stimuli send by our receptors. The receptors send the information to our control center. Control center, hypothalamus in this case, determines what has to be done and sends out a response to the sweat glands over here, or to our muscles over here, so that over here we shiver to bring our body temperature back up to where it's supposed to be. Here we sweat to bring our body temperature back down where it's supposed to be. And in positive feedback, we start with receptors sending signals to the brain. And here in this case, so there are 3 types of positive feedback that our body has. We have positive feedback of labor and delivery, positive feedback of nursing, and positive feedback of blood clotting. This is the labor and delivery positive feedback. It's probably the most famous positive feedback loop. And so the baby is in the cervix, or cervix. The baby is in the uterus. At the end of the uterus is the cervix. And on the cervix, we have receptors. Those receptors feel pressure. So when they feel a lot of pressure, they send signals to the brain, specifically to the hypothalamus. The hypothalamus then will take the information and determine that we need to release oxytocin. So oxytocin is going to bind to the receptors in the uterus and cause contractions. The contractions cause the uterus to get smaller, so they squeeze the baby towards the vaginal canal, causing the head to hit harder on that cervical canal. So as soon as the head hits the cervix receptors in the cervix send more information to the brain, specifically the hypothalamus. Hypothalamus takes that information and tells the posterior pituitary gland to secrete more oxytocin. Oxytocin then moves back to the uterus, which stimulates more uterine contractions. So this occurs continuously until the baby is expelled from the body. That's that climactic event that we're talking about. So this is an example of a positive feedback loop. Positive and negative feedback can be very confusing. I will post another video on positive and negative feedback that you can use if you're struggling with those terms and with how they work. In my next video, we're going to talk about the language of anatomy and physiology, okay? So I will see you guys a little bit later. Bye.